So we've just finished our introduction into limits, and we understand that limits tell us what happens to the y values of the function as x approaches some given number a. Well, it's also important to recognize that there are also cases where there is the non-existence of a limit, and that's what we're going to cover here. There are three, and only three reasons for the non-existence of a limit. Case number one. If the limit of f of x as x approaches a from the left does not equal the limit of f of x as x approaches a from the right, the limit as x approaches a does not exist. Let's take a look at what this means graphically. Here I have some function y equals f of x, and we are asked to evaluate the limit of f of x as x approaches 2, and again, this little minus sign means from the left-hand side. Well, here we have x equals 2. If we are on our curve and our x values are approaching 2 from the left of 2, what is happening to the y values? Well, as my x values get closer and closer to 2 from the left, the y values get closer and closer and closer to 4. Therefore, the limit of f of x as x approaches 2 from the left is equal to 4. Well, what about the limit as x approaches 2 from the right, as denoted by this little plus sign? As I'm traveling along my curve and my x values are getting closer and closer and closer to 2 from the right side of 2, well, what are the y values? The y values are actually always equal to 1. Therefore, the limit as x approaches 2 from the right is equal to 1. So what does this mean about our general limit? The limit of f of x as x approaches 2. Well, because the limit from the left and the limit from the right give us two different values, we simply say that the limit as x approaches 2 of f of x does not exist. Okay, this is case number one for the non-existence of a limit. Notice again, because the limits as x approaches 2 from the left and right are different, we conclude that the limit as x approaches 2 does not exist. And the abbreviation that we use when this happens is DNE. Does not exist. The limit as x approaches a from the left does not equal the limit as x approaches a from the right. All right, that is case number one. Case number two for the non-existence of a limit. If the function increases or decreases without bound as x approaches a, the limit of f of x as x approaches a does not exist. So increase or decrease without bound. That means there is no boundary on the top or the bottom of the function. In other words, the function is going to continue to go up and up and up, or the function will continue to go down and down and down. Let's look at a graphical example. Here I have some function y equals f of x. We have the limit as x approaches 2 from the left of f of x. So what do we notice here? Here is x equals 2, and you might recognize right off the bat from this graph that we have a vertical asymptote at x is equal to 2. All right, we've talked about vertical asymptotes before. Notice that as we travel along this curve and as my x values get closer and closer and closer to 2, what happens to the y values of this function? Well, they continue to go up and up and up towards positive infinity. And because positive infinity is not a real number, our y values are not approaching a single unique value, we say the limit of f of x as x approaches 2 from the left is equal to infinity, and we also write DNE. The graph is going up and up and up. The limit does not exist because the function is increasing without bound. Similarly, we could evaluate the limit as x approaches 2 from the right-hand side. So I'm traveling along my curve and my x values are getting closer and closer and closer to 2 from the right. Well, what are the y values getting closer and closer to? Again, the function is continuing to go up to positive infinity. Therefore, we write infinity, and we also write DNE. Does not exist. The limit does not exist. So what can we conclude about the limit as x approaches 2 of f of x? Well, from both sides, the graph is going up to positive infinity. So we're going to write infinity, but we are also going to write DNE. This is case number 2 for the non-existence of a limit. The function increases or decreases without bound as x approaches a. Let's take a look at another example where this happens. Here, we have the graph. of another function. Let's call it y equals f of x, and we are asked to evaluate the limit as x approaches -1 from the right. Well, what do we notice about this function at x equals -1? Well, we have a vertical asymptote again. And so as I am traveling along my curve, as my x values are getting closer and closer to -1, what are the y values doing? They are going down and down and down all the way to, in this case, -infinity. So what do we write as our solution? The answer is -infinity. Here's our function, y equals f of x, right? The limit of f of x as x approaches -1 from the right is going to be -infinity. And again, we write dne. The function here is decreasing without bound as x approaches -1 from the right. All right, one more example where we have a function increasing or decreasing without bound. Here I have another graph. This is y equals f of x, and here we are asked to evaluate the limit as x approaches -infinity. All right, this is known as a limit at infinity. What is happening to the function values as x becomes an increasingly large negative number? In other words, what is this graph doing as it goes to the left, as the x values go to -infinity? Well, I'm on my curve, and as my x values go to -infinity, what are the y values doing? They are also approaching -infinity. Therefore, we put -infinity, and because -infinity is not a real number, we also specify dne. What about the limit of this function as x approaches +infinity? This is saying what happens to the graph, what happens to the y values as my x values become infinitely large. That means as my graph goes to the right. Well, as the graph goes to the right, what does this function do? The y values continue to go up and up and up. Therefore, the limit as x approaches infinity is equal to infinity. And again, infinity is not a real number, therefore we also put dne. The function increases, decreases without bound as x approaches a. That is reason number 2 for the non-existence of a limit. Let's look at our third and final reason for the non-existence of a limit. If the function oscillates between fixed values as x approaches a, the limit does not exist. All right? So what does the word oscillate mean? It means it's going to jump back and forth between two different numbers. Here is a graph that you guys are very familiar with. Y equals the cosine of x. Now, if I asked you to evaluate the limit as x approaches -infinity of cosine of x, right? This is saying what happens to the y values as x goes to -infinity. Well, what is this graph going to do as it goes to the left? The function values are going to continue to oscillate between -1 and +1. And because our y values do not approach a single numerical value, we simply put dne. The limit does not exist. Similarly, the limit of cosine of x as x approaches +infinity. What is this graph doing as it goes to the right? Do the y values approach a single unique number? Well, as the graph goes to the right, it is going to continue to oscillate between -1 and 1. Right? My y values continue to oscillate between -1 and 1. Therefore, the limit as x approaches infinity also does not exist. Our y values do not approach a single unique number. The function oscillates between fixed values as x approaches a. Let's see another example of this. Okay, here we have the graph y equals the sine of 1 divided by x. And if you were to graph this in your calculator, make sure anytime you graph a trig function, your calculator needs to be in radian mode. All right, and we get this funky looking graph. Well, let's evaluate the limit as x approaches 0 from the left of this function, sine of 1 over x. All right, so we're coming from the left of from the left of 0 of our function, and it's kind of hard what to see is happening here. Well, let's zoom in a little bit. Let's shorten up our x-axis, get a little bit closer to x equals 0. And what do we see? Well, we still have a bunch of action going on here. Let's zoom in a little bit more, and a little bit more, and a little bit more. And the more we zoom in, the more we see this function actually continues to jump back and forth between negative 1 and 1, and it will do that an infinite number of times. And if you think about why that's happening, we're plugging in a smaller and smaller number for x. 1 divided by an infinitely small number actually gives us an infinitely large number. So we're going to actually end up with larger and larger values inside of this sine function. And that's just going to cause our function to oscillate between negative 1 and 1 an infinite number of times. And because we do not approach a single unique number, we say the limit as x approaches 0 from the left of sine of 1 over x does not exist. Similarly, the limit as x approaches 0 from the right of sine of 1 over x also does not exist. Again, as we come from the right of 0, the function is going to oscillate between fixed values, go up and down between negative 1 and 1. And because the limits from the left and right do not exist, we can also conclude that the limit as x approaches 0 of sine of 1 over x also does not exist. The function oscillates between fixed values as x approaches a. So, very important. There are 3 and only 3 reasons for the non-existence of a limit. Reason number 1, the limit of f of x as x approaches a from the left does not equal the limit of f of x as x approaches a from the right. 2, the function increases or decreases without bound as x approaches a. And 3, the function oscillates between fixed values as x approaches a. These are the only 3 reasons for the non-existence of a limit. The only reasons why you should put D and E. So make sure, do not make up your own reasons for the non-existence of a limit. If you are evaluating a limit, these are the only 3 reasons you should write D and E. And if I ask you to explain why, make sure you write down one of these 3 reasons. Don't make up your own. So let's see if we can't put this to use using a graph here. Use the graph of f of x to evaluate the following. We have the limit as x approaches negative infinity of our function f of x. This is saying what happens to the y values as my x values go to negative infinity, as the graph goes to the left. Well, what happens to the y values as the graph goes to the left? The y values go down to negative infinity. And because negative infinity is not a real number, we put negative infinity and also D and E. The limit does not exist. It decreases without bound. What about f of negative 4? Now, be careful. This is not actually asking us to evaluate a limit, but simply tell us what is the function value associated with the x value negative 4. In other words, when we plug in negative 4 into our function, what do we get out? Well, we come over here to the graph. When we plug in negative 4 for x, we get out negative 2, as seen by this dot right here. F of negative 4 is equal to negative 2. Now, the limit of f of x as x approaches negative 4. What happens to the y values as the x values get closer and closer to negative 4? Well, if I'm traveling along my curve here, and as my x values get closer and closer and closer to negative 4, what are the y values getting closer and closer to? Well, the y values are getting closer and closer to 5. Therefore, our answer is 5. Let's look at the limit as x approaches negative 1 from the left of f of x. The limit as x approaches negative 1 from the left. So here's x equals negative 1. We are coming along our curve and approaching negative 1 from the left side. As my x values get closer to negative 1 from the left, what are the y values getting closer and closer to? They are getting closer and closer to 2. The limit as x approaches negative 1 of f of x. Our general limit for x approaching negative 1. Well, we saw the limit from the left as being 2. Let's look at what happens as we approach negative 1 from the right side. Well, as we approach negative 1 from the right of negative 1, the y values are actually equal to negative 3. So the limit from the left of negative 1 and the limit from the right of negative 1 are going to be 2 different numbers. And because the limit from the left does not equal the limit from the right, the limit as x approaches negative 1 of f of x does not exist. Again, the left and right side limits are different. f of -1. Again, this is not a limit problem. This is telling us what is the function value associated with the x-coordinate of -1. Well, when I plug in -1, we are going to get out 2, as seen by this closed circle. Notice we don't get out -3 because down here we have an open endpoint, an open circle. The limit as x approaches 3 from the right. Here I have x equals 3. If we're traveling along our curve from the right of 3, sorry, that would be the left. As we're traveling, ignore that. As we travel along our curve from the right of 3, what do the y values get closer and closer to? Well, the y values get closer and closer to -1. Therefore, our answer is -1. What about the limit as x approaches 3 of f of x? Well, we just saw the limit from the right was -1, but what happens as we come from the left? Here we go, this is from the left side now. The limit from the left is actually equal to -3. And because the limit from the left and the limit from the right are different values, the limit as x approaches 3 of f of x does not exist. And what is f of 3? Well, f of 3 is the function value associated with the x-coordinate 3. When I plug in 3, we actually get out 5, as seen by that dot right there. And finally, one last one. The limit as x approaches 5 of f of x. Well, what is the limit of f of x as x approaches 5? Here I have x equals 5. As I'm traveling along my curve and my graph gets closer and closer, my x values get closer and closer to 5. What are my y values getting closer and closer to from both sides? The y values from both sides get closer and closer to 3. Therefore, we can confirm that the limit of f of x as x approaches 5 is equal to 3.